Hi, this is a recording of me using COMSOL to perform a simulation for the Bioengineering 167 Medical Diagnostics class. So in this first of 3 videos, we're going to be making a binding-based biosensor that relies purely on diffusion and diffusion alone to transport target to the surface of the sensor. So we'll start by getting the VPN going in the background. And then once that's done, I will launch COMSOL. I'm using COMSOL 5.4 here. That's the latest version as of November of 2018. You can do this with earlier versions too if need be. Okay, and so here's our default COMSOL window. So we'll start with the model wizard. I'm going to select a 2D space for this simulation. And then in this model here, we're going to use chemical species and transport of dilute species alone. So we're not going to add laminar flow in this one because we're only going to rely on diffusion to provide target to our binding-based sensor. So I'll add that physics to my model. All right, I'll hit next. And now in this case, since we're using diffusion alone to transport target to our sensor, we can't use a stationary simulation because the simulation would actually never converge to a value that's at equilibrium. So instead, we're going to use a time-dependent simulation. We'll be able to look at the progression of the binding and the amounts of target left in our sensor over time. So I selected time-dependent and click Done. And so here's our default model. So the first thing I'll change here are the length units. I'll change that to something a little more logical for a microfluidic sensor, so like 1 millimeter. I'll zoom out a bit so I can see the overall scale of the device that I want to draw. And then I'm going to draw my device using 3 rectangles. So I'll draw this and then you'll see what I mean in a minute. So the first rectangle is there in the middle. The second one will be here a bit to the right. The third one a bit to the left. Okay, now this is going to represent a single microfluidic chamber that I'm going to load my sample into, but I drew it in 3 sections just so that I would have easy access to these different boundaries. We're going to define our sensor to be this surface here, this boundary shown here, where I'm showing with the mouse pointer here. And so this way, in drawing it in 3 pieces, I can select that boundary in a minute. Okay, so it's drawn my sensor here. It's 1 millimeter by 1 millimeter little region here with a 1 millimeter across sensor here at what would be the bottom of the channel if you imagine this as being a cross-section through a 3-dimensional chamber. Okay, so the next thing to do is to assign a material to it. I'll right-click on Materials and select Add Material from Library. Under liquids and gases, liquids, we're going to select water for this demo. Of course, you could always make a custom material if you're doing something with blood or urine or some other liquid. All right, we'll click Add to Component, and in a minute, our component should turn blue and all of those domains should be active over here, showing that the water has been assigned to all the domains of my sample chamber here. So that's great. Okay, so here's my physics module. Under transport of dilute species, I'll step through this and look at what the defaults are. It has convection enabled, that we're not going to take advantage of that. Under transport properties here, we see that there's no velocity field defined inside of this, so that's as expected. This sensor is going to rely on diffusion alone to transport my target to the binding surface down here. All the boundaries initially default to a no flux boundary condition, which is correct. And the initial values throughout my system here are concentration for my solute C of 0 moles per cubic meter. I'm going to change that to 1 mole per cubic meter, or I think that's 1 millimolar in more normal concentration units. And so we're going to use that as the starting concentration of our target. So if this were, say, a blood glucose sensor, that would represent the concentration of glucose in the blood that we load into this chamber at time equals 0, and it would be present at 1 millimolar concentration. And then some of that will be consumed over time by our sensor, which is, of course, this surface here. So there's that. So at this point, I've actually done enough that I should be able to run the simulation. But first, I'm going to look at the mesh and build it. And as I suspected, it defaults to a really coarse mesh for this sort of thing. So I'm going to increase this all the way up to extremely fine, so we have a slightly nicer looking simulation result. Okay, so I'm going to right-click on Study 1 and run the computation, and we'll see what we get. Okay, good. As expected, we see a sea of green representing, as we see over here on the color bar, a 1 mole per cubic meter solution throughout my system here. And I could step through time, but nothing's changing because no binding is occurring. So the next step is to apply something that would turn this boundary here into a surface where binding can occur. Now in our model here, we're going to use a very simple model of binding where if a target, a molecule of the target solute in this sample, if it bumps into this surface here, it sticks, and it sticks forever. It sticks permanently. So it's an irreversible, simple model of binding. Later on in the class, we'll look into more realistic models of binding on a biosensor, but for now, this is a good start. So I'll right-click on Transport of Dilute Species, and under Surface Reactions, I will select Fast Irreversible Surface Reaction, which basically encompasses all the assumptions that I just described. Then while this selector is active, I will click on that domain. And then the one thing to configure about it here is the stoichiometric coefficient of this binding reaction. I'm going to change that to -1. The minus sign tells COMSOL the direction of flux or binding. In this case, a negative sign indicates that the solute is going to be moving from inside to outside of the domain here. And the 1 here just sets a simple kind of unimolecular stoichiometry for our binding. Okay, so I'm going to right-click on Study 1 again and click Compute. And we'll see if things change. Okay, they do. So this time I can see the red color here indicative of my 1 mole per cubic meter starting concentration of my solute. You can see that the very large bulk majority of the chamber still has that concentration in it at a time point of 1 second into my simulation. And then we see the range of concentrations down to 0 moles per cubic meter. And I can see that some binding is occurring here right on the surface of the sensor. I'm going to zoom in a little bit. Not that much, about that much. And we can start to see that 1 second into the simulation here, we have depleted a very thin plane of fluid on top of that binding surface there. We've depleted it of its target, and so that's why we see the colors, the non-red colors down here. Now, before I go any further, I'm going to remember to customize something about this plot. Now, as we bind more and more target to this sensor here, eventually we won't have the solid red present here as we start to exhaust more and more of the target from the solution. But I don't want COMSOL to automatically rescale the color bar over here. If it does, the results will be really hard to interpret. So early on here, to force it to not do that, I'm going to click on my surface concentration here. And then under range, I'm going to select a manual color range, and then the defaults are correct. I want it to run from 0, a concentration of nothing, to 1 mole per cubic meter, which was the starting concentration, this dark red color over here. So there, now once we've done that, I can simulate over and over, but COMSOL will never lie to me by changing the color bar scale over here. Okay, good. So we are, looking back at the results, we are 1 second into our simulation here, and we see this thin little layer of my sample has been depleted of its target, of the red material shown here. So let's go back under the configuration of this study here and simulate a longer time period. So here you see the MATLAB-like expression that tells COMSOL what time frame to simulate. We started here simulating from 0 to 1 second in 0.1 second intervals. I'm going to change that by 1 order of magnitude, and now we're going to simulate from 0 to 10 seconds at 1 second intervals, and we'll see what effect that has. So every time I change this, we're going to look at an order of magnitude longer time frame and see what effect that has on the operation of our sensor. So here's 1 second, and then as I step through this, I'll talk through the times that we're looking at here. So at 1 second, 2 seconds, 3, 4, 5, 6, 7, 8, 9, and finally 10 seconds into the simulation. That's the last time point. And so from that you can see the depletion zone over that 10 seconds of simulation is growing, but it's clearly in a regime here. This is the first of 3 regimes we're going to try to highlight and actually give a name to. It's clearly in a regime where there's only a plane lying low on top of the sensor surface here. There's only a plane of the sample that's being depleted of the target molecules, of the red stuff here. So what we'll say here is in the early time points of the operation of this diffusion-based sensor, the depletion zone geometry is what I would describe as planar. So imagine this is a slice through what's ultimately a 3-dimensional channel that has my sample in it. And so what you're seeing here in this dark blue color is a thin plane right on top of the surface of the sensor, which at 10 seconds has been largely depleted of its target. And then we have diffusion providing fresh target to that over time. So to highlight that shape further, I'm going to add one little customization to my plot here. In addition to the surface that shows the concentration, I'm going to right-click on this and also add a contour here. And I'm going to specify a single level of concentration that I'm going to draw a line on, kind of like a topo map. And so this is going to be at 0.5 moles per cubic meter. That's the midpoint concentration. That's halfway down, halfway between the starting concentration, which is the red stuff here, and 0, which is the dark blue color down there. Then I'm going to change the color of that line to be a solid black line. And then when we plot it, there we are. We can see that on here. Let's see if I can play with that. No, I guess that's an okay level of zoom. So this dark line here is basically the marcation line between concentrations of our target that's above 0.5 moles per cubic meter and concentrations that are below it. So everything below this line here has been depleted of more than half of the target molecule that was in the starting solution. So basically, by looking at that shape there, we can sort of describe the shape of the depletion zone as time goes on. Okay, but in these early time points, at a time of 10 seconds, we can say that we're in a planar depletion zone where we have largely not depleted the bulk of the sample volume of the target that we're trying to capture, of the glucose, for example, if this were a blood glucose sensor. Okay, so let's go another decade further in time. I'm going to change from what I started with to going up in increments of 10 seconds to 100 seconds now. Let's run the computation again, and then I will step through the different time points. So here's 10 seconds, 20, 30, 40, 50, 60, 70, 80, 90, and finally 100. And so now as time's going on longer and longer, we can see an interesting evolution happening. What was once a thin plane of depletion of these dark blue colors is now sort of becoming this dome shape. It's starting to transition into something else. And so we'll name that in just a minute, but let's first go a little further in time. Now we're going to go in 100-second intervals all the way up to 1,000 seconds. So let's compute that again. We'll start on 100 seconds again. There it is. And so now we're going to go to 200 seconds. So twice the simulation length right there. 300, 400, and finally 500 seconds. So now you can see something very different is occurring. The shape of the sensor right here is not as evident anymore. Instead, above the sensor, we see this sort of half circle or what we'll call a radial shape depletion zone, where because of basically the ratio of the size of this depletion layer here to the size of the sensor, the area of the sensor is less important. What's more important now is sort of the height of this depletion region above it. And so that lends itself to what looks more like a radial depletion zone instead of the planar one that we started with. So at 500 seconds into this particular simulation, we see this shape emerging. This half circle here is now the region below which we have depleted our sample of the red target material. Now there's still some regions of red here indicating regions where we have not depleted much of the target, but the region of depletion has grown considerably at these longer time points. So let's keep stepping through. 600 seconds, 700, and you see right there something very important happened. These lines of 50% concentration remaining actually reach the top of the channel. So this marks the transition from that sort of radial shape to our third regime, our third shape that we're going to describe, which is a linear depletion zone. Linear meaning that now the zone of depleted material is going to be starting to not just grow upwards in this direction, but it's actually going to be going up left and right in a linear shape up and down the channel. And so that's the third and final shape that we're describing. So I'm going to zoom out here so we can see more of the channel as this happens. When I zoom out now, you can see that there's still a lot of the channel up here and there, that the concentration of our target hasn't changed much. But now we are depleting a zone that's growing in a lateral or a linear direction to the left and the right, and over very long time points we will continue to deplete the sample in these regions here as those molecules diffuse into and ultimately are captured by our sensor. All right, so there's 700 seconds, 800, 900, and finally 1,000 seconds. That's the last time point in this set of simulations. And we can see now that these lines of 50% solution depletion are nearly vertical, showing this full transition now. So now the shape, the side of this where the sensor is located, is actually kind of becoming less and less important. Now instead the area that's important is this area in here, and this area in here, because those are the areas that are the rate limiting step. The size of the channel here and here are what are specifying the flux the rate at which the fresh red target here is being transported by diffusion into this region here. For capture. Okay, so let's do one more set of time points. We're going to go up by 1,000 second increments to a total of 10,000 seconds. Run the computation. And there's our result. So here's 1,000 seconds. When we step to 2,000, we'll see a huge difference right there. So 2,000 seconds, a very long period of time for the sensor to operate. We have depleted the entire sensor volume at least somewhat. These regions here are nearly half depleted. There's the line of half depletion, and you see it continuing to move to the left and the right. The shape of the depletion zone is now linear. It's a line spanning from here across to there, and that's going to keep growing as the time gets longer and longer. Here's 3,000 seconds, 4,000, 5, 6, 7,000, 8,000, 9,000, and finally 10,000 seconds in, we have a near complete depletion of our red target at this extremely long time point. But, you know, this is a diffusion-based transport, and due to the random walk nature of diffusion, there's still always a few target molecules lingering in this region, so that's why we couldn't do anything but a time-dependent study on this. So there's still perhaps a vanishingly small amount of my target left in this region here, but at these very long time points, we can say with confidence that we have consumed pretty much all of the target that was originally present in our biosample. Okay, that's the first video, and so it will continue with the second video to show you a model microfluidic system that relies only on convection to see flow and see how that affects flow within the system. All right, bye for now.